Alright everybody, it's Adam Hurt again with 973 Ramp. Welcome back. And we are going to continue on this West Coast drive. So if you're coming right out of that previous video, see we've actually done quite a few things here. I got some feedback to the last video. Maybe I spent a little time doing things that were a little redundant. And I think kind of all the stuff I did here would have taken a long time to do on video, and it's a lot quicker to show you what I did after the fact, and I think everyone will still learn that. So I'd love to get some feedback on how these videos are, so I can do better ones for you in the future, because I don't want to waste my time and I don't want to waste your guys' time. And I'd like videos that are good to watch and easy to use. Did a lot of things here. Added the gearing in the gearbox, missing standoffs, added sprockets, tensioners, chain. All the wheels are now locked in place. I am missing shafts though. There's some lessons I want to teach as we do the shafts, so I will draw the shafts. Maybe we'll do the standoffs in this video. I don't know if that's the most useful exercise, so maybe I'll just do that and post a follow-up of the finished robot. And haven't decided how we're going to post CAD yet, but we are going to post all the CAD for our videos, and if we do a video on something else, we'll post whatever documentation or stuff to go with it. Alright, so let's jump in. So I think I'm going to start with the gearbox. So open that up. I know in the last video I commented that an inch and an eighth apart is great for two Vex gears, and that is true, except I forgot about the chain. So the first point I'd like to make here is when you do get these CAD files, you'll see that the distance from this plate to this plate is actually not directly dimensioned. That may seem counterintuitive to some, but for this kind of gearbox, if you're making this, you're making your own standoffs most likely. Or even if you're not, my point is somewhat valid, and you'll see that in a moment. I like to use the components in the assembly and their various spacing constraints to figure out what these plates need to be. Let's say I still wanted to come in and make these nominal standoffs. Well, at least now I have a good start, and I'll adjust the next nominal. Because let's say you guessed the nominal size from the beginning. If you're wrong and have to go back and iterate that 10 seconds you spent making that first mate is wasted, and I really don't like wasting that kind of time. I know that sounds real small, but it all adds up. So what I did is, this gear has made it to that bearing, and this gear's made it to that. I love that Vex has the planes of their gears properly spaced, so the plane is on center. So this gear has made it to the center of that. Yes, we could move it over a little bit and make this a little narrower, but I like putting stuff on center. Sprocket has made it to that, sprocket to the next sprocket, and then I did a 3/16 spacing from this sprocket to the face. That is pretty close, and our chain model makes that look pretty close, but that does work. If you ever have concerns, though, a 1/4 inch spacing is not a bad idea. You're certainly not going to lose regionals because you added a 16th gap to your chain. So what else did I do here? Oh, in the first video I made this bearing a hex bearing. We don't do that here because, one, we didn't have great access to hex bearings last year. We bought like 40 at kickoff and then realized we couldn't get any more. And two, most of our kids know how to machine, and bearing rounds are one of the first things they learn, so that's easy for us to do. And we do a similar trick on the wheels for that. It saved us like $20 per robot, so I don't know that it was really a money savings, but it did free up some hex bearings. So not much else going on in the gearbox, I don't think. Alright, so we're going to leave the gearbox for now and look at some of the other things. So this chain model is something I reuse all over the place, and how I generate this is I just come in and draw the pitch diameter, and I use offset entities and do the center to center. You can do it for different pitch diameters too. Obviously, both halves of this are made to be the equal or the same. And then I extrude that to some number. I don't remember what that number is because I copy and paste this file every time. I guess I have it at 320. It's something we've just measured chain over the years, and these have worked for us. I wouldn't hesitate to make your own version of this a little larger, bigger in diameter and wider, to help exaggerate any clearance issues if you do have some. And let's see if I did this. I do like assigning mass properties for this. I have not actually. I had an older one of these chain guys that I used to use that was driven by a design table that would also set the mass. Generally during season we will come in and set the mass on those. Now, I want to say 25 chain is nominally 0.1 pounds a foot. I just like having that stuff accurate. So next thing I want to show, I'll just say it, I won't open the CAD file. The front plane of that chain, you guessed it, is on center, and that ties into the next point. Vex did score points with me by having the front plane of their gear, maybe it was right plane, I don't remember which, centered on the teeth, but they did not do that for sprockets it's there. So I added this plane. In hindsight, doing a body move so that the front plane, just that's a little more intuitive, probably would have been a little cleaner. And I use this plane to come back in the assembly, mate the center plane of that chain with the center plane of the sprocket, and now, based on the sprocket spacing we did here, these outer sprockets are spaced. So once again, I didn't dimension these sprockets at any distance, I didn't make a spacer, I didn't do any nominal thing. I let them land where they wanted to land, and since it looks like that all works, I'm then going to come in and run with those dimensions and make spacers to match that. If you did want to use nominal spacers, there's some argument to that, and you could kind of do the inverse process there. The way this drive is laid out, at some point something's got to give, and I don't think you can use nominal spacers everywhere, but for us, making spacers is not a big deal. And if you're only making one of these drives, sanding spacers or something wouldn't be that crazy either. So what do we want to look at next? I did add these tensioners in. The hole for that is, I'll show what I did there. You can look in the original sketch. I have a small hole, 100 thou, just so it's obviously small, so that I get the placement of that hole in the initial sketch. But then because that is a countersunk hole, and I do want to show that, I did use Hole Wizard after the fact. I kind of do Hole Wizard wrong in a lot of spots, and I do it right in some spots, so I don't know that you want to trust everything I do there. I think that covers kind of all the changes I've did. If I missed anything, feel free to point that out or catch that in the CAD when I post that in a couple days. So now we're going to come in and do shafts, and there's our team does a lot of hex shafts, so we're CADing a lot of them, and it's an easy part to make really funky, and it's an easy part that off the top of your head right now you may be thinking you can't make that in one sketch, and we are going to do that. So this is another one I think that some people might find silly or wrong, but it works great for us, and I really like it. So first we're drawing the top shaft in that gearbox. It's just a 3/8 hex in the center with a bearing round on each end, and we're going to add a snap ring groove in later. For this specific type of shaft and snap ring groove, I like to add the snap ring groove in a second feature. I know that's crazy, hypocritical, yada yada, but forgive me. So you see I'm using a lot of construction geometry again to delete as many dimensions as possible. And even though this is a 3/8 hex and it's a 3/8 round, I'm going to dimension this at 0.1 for now, and you'll see why I do that in a moment. And I think this is 1.83. Make this, actually, it's in the sketch. Make this centered because everything should be symmetrical, and do revolve base to exit this out. Now, for stuff that's real simple, I won't name my features every time because I don't name features for the sake of naming features. I name features so that future Adam or other people can edit parts and understand where stuff is. So if a part is immediately obvious, then I don't feel you need to name the feature and waste that little bit of time. At work, however, we name our features on everything. That's just what we do. So kind of did that without talking about it. I came in on that face, made a co-radial mate between the polygon I drew and the boss so that its size is set by that first sketch. Made it horizontal just because I don't like stuff floating free, and then I extruded it up to surface. So this feature has no dimensions. It is entirely determined by this feature, and the reason I did this 0.1 is just to make it easier to grab that face and draw on it. So I'll come in after the fact to make that really small. So now we have a hex shaft that you can come in and do this. And this works with multiple bodies, multiple hexes. Obviously each hex showing that takes another feature, but they can all be laid out in one feature. And this is wrong in some ways, but it works great for the team, works great for FRC, I think. Because I love having that first feature do everything. I can't reiterate that enough. Putting chamfers on here. I like showing them in CAD just to help reinforce the fact that we do them. I feel that pretty much every shaft that goes through a bearing in FRC anywhere should be chamfered. Even if you do not have a lathe, you can put it in a drill chuck, like in a hand drill, run it against a file, run it against a sander, spin the shaft by hand against a sander. You can do those chamfers will really save you a lot of hassle, so I feel it's real important to do them. So we're going to save this as gearbox and immediate shaft, kind of skipping all of our part number conventions, and I think that's appropriate for now because that's a whole nother bag of worms. So now we're going to come in, put this shaft in. Want that the other way. Oh, where's my shaft? So if you were to come in and measure the distance between the bearings, it comes out to 1.844, and I made this 1.83 if you're paying attention there. So that's 14 thou short. That's good. That gives you some leeway for manufacturing tolerance. Making this any tighter won't give you any benefit, so it's nice to make things loose where you can. I mean, there's designing something that requires tight tolerances everywhere doesn't make you a good designer. It just means you can tolerance things tight, which I don't see a benefit to that. So the better designer can make stuff loose and still have everything work. So now we're going to come in and draw the snap ring. So for the middle of a hex, we actually use the next nominal size snap ring, which in this case would be 7/16. In most of our hex sizes, this works out well. Got that number wrong there. For the 3/8, it's a little shallow, and I've debated switching to 10mm snap rings, but probably not going to because that's another part to have and that sort of stuff. So I'm just going to guess this 1-inch spacing now and cut this groove and see how it works out. And you'll see that you only get a slight cut, and that's actually totally fine. This works. This worked on our robot last year. We do this all the time. This is just so much easier to get to as the assembly person than a full 3/8 step snap ring, which would be, smaller diameter than that. And it's just less stress risers you're putting in your shaft, which is nice. So we can see I actually got, well, I wasn't close at all. You can see that's under the gear. So we're just going to iterate that number. Usually I'd like to get in there and measure, but sometimes I feel real lazy and we'll just change it so we can get it to measure. See what this number is. That's 19 thou. Maybe we'll pull 10 thou out of that. Even though that totally would work as is. Alright, so now we have an intermediate shaft. Rebuild. Did that not move, or did that go the wrong way? It did go the wrong way. So, like I said, I make mistakes all the time. Cool, so that shaft's done. Another thing to do would be the output shaft here, so let's start on that. This one points out a little more use of construction geometry and is a little more complicated at first. So on the left side we have a snap ring groove, to a 1/2 inch bearing round, to a 1/2 inch X, to another 1/2 inch bearing round. You'll see why we do that in a little bit. To another snap ring groove. And I missed the vertical on there. So I want these to be collinear equal. I want these 4 to be collinear. These 2 to be equal. And these 2 to be equal. Actually, there's some argument maybe later you make to not having those equal, but not a big deal for this video. And of course you should have all of your snap ring groove sizes memorized. But if you don't, McMaster actually has them pretty easy to get to under the product detail tab on their snap rings. And I'm just going to guess a lot of these lengths again because usually I have a little better idea of dimensions coming into things than I do in these videos. But if you don't, there's no hesitation in just guessing something and coming back and iterating that. And I made this center body dimension. Maybe it makes more sense to dimension between the bearings. Not a huge deal for this video. As long as you guys are tuned into, you should dimension kind of what makes the most sense for whatever you're iterating. So once again, I'm going to come in and draw this hex. Make that co-radial, make that horizontal. You could make it vertical, but just do horizontal, doesn't matter. Up to surface, and then come back in and edit that first sketch. And you technically could start with this at 1/10, but it just makes it really hard to come in and draw the feature that we just did. Alright, so now that we have this modeled, we're going to put this in the assembly. And you'll see what I was talking about in the first video about snap ring grooves and that bearing being backwards to hold that in. So this snap ring would keep the shaft from coming out this way. And I noticed we missed chamfers, so just to drive the point home that everything should be chamfered, do that. And you notice you can click the face, you don't have to click the edge, although I missed it at the edge that time. Oh, no, it's because I'm hitting the edge behind it. Oh, now I'm looking all sorts of amateur. Usually I'm pretty good about hitting the face, and that saves a lot of time. Or saves 2 seconds, not a lot of time, but that adds up. So we'll come back into the top level assembly and measure that. Some people would complain that, oh, that's not good, that's loose. How did that mate that back up? Oh, because that was probably mated to that other bearing, yes. Some people might complain that this is not mated to that. I don't think that's a big deal, and it just wastes time to fix that. But if that bothers you, you can come back into my models after the fact and fix that for me. So now I'm going to measure, and I'm just going to hide this wheel actually to make it easier, and I'll measure off another wheel. Hide components is one of my favorite ways to get in to measure stuff because it's so easy to undo. Transparency kind of bothers me on some things, so I don't like doing that. So I'm going to measure off that snap ring face to this outer bearing. And I'm getting 1.282. So I'll probably make the shaft 1.3 longer because, you know, there's some slop in those Vex wheels. Our manufacturing slop, all that adds up. Much more though, and you'll probably start running into trouble with throwing chains. Although on the center wheel that doesn't affect, the spacing here doesn't affect our chain on this shaft. I don't know why my measure's not going. Don't know what's going on there, so I'm going to save and rebuild, which is, oh yeah, it wasn't letting me measure because it was waiting for a rebuild. And some people commented that I don't use any keyboard shortcuts and I could save a lot of time if I did, and you are right. I use the hell out of keyboard shortcuts, and I have a mouse with a bunch of buttons that I've mapped a bunch of keyboard shortcuts to. But if I did that for the videos, you guys couldn't see what tools I'm selecting, so I decided not to do that. So yes, you are right, keyboard shortcuts are great. I very much agree with you guys on that. So now we will do a very similar process to make the outer shaft. Yeah. Or actually, I think we'll skip drawing the outer shafts. I'll just say that the outer shafts are a good place, since you can tell one is a little bit longer than the other, to use configurations. I'm going to have a video dedicated just to configurations, all the dangers that are there. Configurations can cause a lot of problems if not used right, but there's a huge potential payoff if they are used right, and a huge time savings. I'm sure there's a lot of people doing things really manually now that could be saved with configurations. And then there's also some gotchas that configurations might wreck teams that have part numbers for everything, and have unique files for everything. And there's a trick I do that's really ugly or really elegant, depending on how you look at it, that helps get around that problem. So I'll let you guys on your own do those outer shafts and come in and do standoffs. I'll just say the dimensions of these standoffs if anyone's really interested in them. This upper one is a 3/8 tubing we buy off McMaster that has, I want to say, a 235 thou ID. That's something we ripped off of 254 a while ago. And this bottom one is 3/4 OD, 16th wall, whatever that ends up as. We don't get that off McMaster. We just get that with a regular metal. But McMaster does have that or something similar. But you don't have to use those numbers. You could do whatever and change the bosses. For spacers, I do not like to use hex broach spacers because it's just a lot of extra work. We have a couple drill sizes already pulled out in shop that correspond to the slip fit over a 1/2 inch, the slip fit over a 3/8 in terms of hex. So all of our spacers actually are straight, and that really saves a lot of manufacturing time, and that's never really been a problem for us. We have the round size drill that is a nice fit. So unless I'm forgetting something, I think we finished this drive. And the point of these videos really wasn't the drive; it was to show kind of an overall strategy I use for doing the basic design. And obviously the big takeaway here is do as much as you can in that first sketch where it makes sense, and for when you want to come in later and delete parts from an assembly and that sort of thing, kind of mate stuff to itself as much as possible. Damp Robot on Team 100 recommended the copy with mates tool. That's something I did not know about, and actually would have been good for some of the things I did here, and I'm going to do that again in the future, or I will do that in the future. And it's always good to hear stuff like that. You really can learn something about SolidWorks from almost anyone. So I always like to ask that question when I meet someone. What's your favorite SolidWorks trick? So if you have any questions or you feel I missed anything, let me know. That's the end of this video. Thanks for tuning in, and good luck.